Okay, all right, great. So yeah, so first and foremost, I want to thank Rositsa and Moshe for organizing this wonderful workshop. And I guess what I'm gonna tell you guys about a little bit about today is a little bit about transformers and what they can express, yeah, and the connection to formal language theory. And this is collaborative work with the following people. And the work that I'm going to be presenting is mostly the one from ICLR 2024. And maybe one thing super quickly that I want to mention, because I think we are a little bit over time, so I'm going to try to just gloss over some details, yeah. And trust me, if you're not convinced about something, we can always check it later on, yeah. It's just mathematics, so. Okay, all right. So first and foremost, you heard transformers already from Armando's wonderful talk. And I'm pretty sure you guys have tried ChatGPT as well, and how wonderful it is, yeah. So this model is basically based on this paper, Attention is All You Need. And now it's been popularized by all of these large language models like GPT-4, Gemini, and so on and so forth. So a transformer is a sequential model in the sense that the input is a sequence. So it's unlike classic feed-forward neural networks. For example, it could be a sentence. Something like Kaiserslautern and Frankfurt are both located in Germany. You can also have time series. You can also have a video, audio, and so on and so forth. And you can also have an output, and it's also another sequence. And now the question is, despite the anomalies, despite the success of transformers, there's been a number of anomalies that people have detected. So for example, and basically these are associated with the problems with learning simple concepts. So for example, in these two papers, they showed that it's been quite difficult to train a transformer that recognizes a really simple regular language. So this language just simply says, basically just want to count the number of A's in the string, right? So the question is like, why is it difficult? And is it even expressible by a transformer? And if yes, is it trainable by existing learning algorithms? So all of these are relevant questions, yeah. So let's just give it a try a little bit. So I did actually try this before the talk. Maybe this is not the best run. Sorry, I don't know if you can read this. It's a little bit small. I just noticed. So I tried this using GPT-4, and this is a shorter version of the entire conversation. But I'm trying to just ask GPT to just count the number of A's here. So I did feed a bunch of strings, yeah. And then what happened is that, and then I asked this, okay, so is this, does it have even or odd number of A's? And then it says it has odd number of A's. Input string has 19 A's, and which is an odd number. And then you can check this using Python, and it turns out that actually it has 22 A's, which is an even number. Okay, so I'm not saying that this is the perfect way of doing this, but you can try this and you can make the strings larger and larger, and seems not. Say again?
You don't need Python, you can count them yourself.
Of course, sure, indeed. Right, of course, that's actually the right answer. All right, so. Again? So yeah, so this is basically, so the field of formal languages and neural networks, FLAN, grew out of such questions. So now it's been quite a lot of people working on it, and it's a rapidly growing community with a rapidly growing number of publications at ML venues. And the focus so far, I should mention, is expressibility, not really trainability. And we study different transformer architectures, and we want to show an expressibility of certain concepts in the with respect to the architecture. And as you will see soon, the main key techniques here are circuit complexity, automata theory, and logic. And I will give you a teaser for the kind of stuff that, the kind of results that are around, with, of course, a bias towards my results, understandably. So I'm gonna start with formal models of transformers. So the input, as I mentioned, is a sequence of symbols, and let's say over some alphabet sigma, let's just say for now A and B. So the first thing you do, you need to preprocess this. You need to convert this string into a sequence of vectors. So that is what you do is that each of these UIs is going to be converted into a vector in some in RK. And you also need to have some kind of so here I put F here. Yeah, so this is a typical token embedding function. And you also need to have some information on where it is. Yeah, so because you also want to be able to distinguish if does the A occur here or occur here, right? So you need to be able to also distinguish this because you need to put the to give some position information. Now, so a transformer, what it does is simply, so well, you have some input sequence, and then you're gonna output some, you're gonna have some output sequence, and this is length preserving, and you can think of it as a function from, yeah, as a function, as a transducer from RK to, I don't think you can see this thing. It doesn't look very clear. So to RH, yeah. So the dimension can be different, but this has to be length preserving. And okay, so now this is not yet a way to define a language because you just given an input string, you output some string. So you can just do something simple to check whether or not this one is accepted or not. You can just do something like, for example, you can define some vector t, yeah. And then you just want to check if this symbol at the beginning here satisfies something. So for example, like it's less than 0. Okay. So you can also do it at the end if you want. It doesn't matter. Doesn't matter. Yeah. And so this TF here, and this T bar here, these are given. These are specification of the transformers. All right. Okay. So this is like the bird eyes view of the transformer, and so that's basically that's the black box. So basically, it actually has a bunch of layers, of course, just like fit-forward neural networks, and each of this layer here is also a length-preserving transformation. And let's take a look at one of this, what it does. Basically, these are given as you have 2 affine transformations and 1 piecewise linear function. So these affine transformations, of course, these are just linear transformations plus a translation. Yeah, and piecewise linear, basically, you can think of it as composition of affine transformations with ReLU, which is basically doing max. Okay, so let's see how. All right, so that's basically how you have this A, B, and N. But how does it compute the next sequence in the layer? Well, what you do is simply, so unlike an automaton, like you process as something from left to right, what you do is that you want to do things in parallel. So given a position, you want to compare yourself with every other person or every other position in the sequence, and based on that, you want to compute some kind of a score that reflects how related you are with another person. So that is, you draw this kind of a matrix, yeah, and for each cell here, you're gonna compute an attention score. So for example, you get some value like this, and in here, what you want to do is you want to identify, for each row, you want to identify columns that maximize the score, out of which compute a vector u. So for example, I don't know if you see the color here, but this is like, so the maximal one, for example, are labeled by red, labeled in red. And the first one here, the maximal one is here. So V1, you pick V2. But now you might have you might need to break ties if there are two guys that have the same score, maximum score. So there are several ways to break ties. So for example, you just pick the leftmost, you can compute the average. So the leftmost one, so for example, here you can compute the leftmost one, or you can just compute the average, which is basically, so by the way, this is called unique hard attention. You can also compute the average, which is simply just take the two guys, okay, V1 and V2, plus, and then divide by 2. Okay, so this is called average hard attention. And as you'll see soon, So different kinds of attention mechanisms give rise to different expressive power. Now, okay, so yeah.
There is no condition that prevents this average from being another value that may have received a small attention value.
So let me go back here.
I mean, possibly the average that you calculate.
So you first need to pick the maximum guys. So for example, these two guys, right? And then you just,
yeah,
so
but when you compute the average, you may, so I need the next slide. So when you compute the average, this average, this U2 tilde, this new U2 tilde may have been in the table with a smaller score.
Yes, it is possible.
And you don't worry about it.
No, so we don't worry about it, no. Okay. At least per definition, you don't have to worry about it. Yeah. Okay, so right, so basically now what have you done? So for every row, you've picked either a column or you pick a summary of the columns that maximize the score. So that is, you've computed UIs, yeah? So now we have U1 up to UN. So what you do now is, how do you produce these guys? Well, you simply have to apply this piecewise linear function on the row, okay? And the new vector that you just computed, okay? So VI and this UI. So that's pretty much it, what you have to do. So that's basically abstract definition. I have a simple example here, and I hope that you don't try to go in to read all of the details in the slides. I'll just give you an illustration of how it works. So in order to get a transformer to recognize this, so what you first need to do is that you need to have an encoding of the A's and B's into a vector. So I'm going to encode A as 1.0 and B as 0.1, so this typical one-hot encoding. Now, you also need the position encoding, and there are different ways of defining this. So here, I'm just going to pick I divided by N. Yeah, so we'll talk about the details later on, but for now, just trust me, we're just going to pick that. So if you have like A, B, 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 A, it's just going to be encoded as the following sequence of vectors, right? So now what we want to do is that the intuition is very simple. So we want to get a transformer to first compute the rightmost occurrence of A's. Okay, so look at the position, and then I'm going to compute the leftmost position of B. I'm going to look at the position, I'm going to compare them. That's pretty much it, okay? Of course, you also need to make sure that there's at least one A, that there's at least one B. So that's basically what we want to do. So we're going to do it in two layers. The first one is we want to forward the last occurrence of A, and if not occurring, we forward the last B, okay? So that is, so first you have this A, B, 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 A. What I want is I want to pick this A here, yeah? So I want to produce this, oops, I think I left something. So I want to pick this A here. I want to forward the original guy plus this thing, right? Forward means I want to compute in the next layer. Yeah, this is basically what it's going to be. That's basically what I forward. So, so I need to, here, if I look at the score here, I need to make the last one to be maximum, right? Okay. And you want to define this matrix, this A and B in such a way that this score is going to be maximized. And what you're going to do is you're just then going to be forwarding this A's and the last guys and itself. Okay, so that's, don't worry about the details, just trust me. And the layer 2, you're going to find the leftmost B, if not occurring, forward the leftmost A. So just the same as before. So what you're going to be producing is, so remember, this is the last A's. And B here is just going to be the leftmost B, which is basically here, just the guy here. Okay, so you need to then just construct this matrices, or not matrix, sorry. This affine transformations A's and B in such a way that this is maximized. Okay, it can be done. Okay, so anyway, so what you got at the end is this is going to be the last layer, And what you're gonna look at is, now these A's and B's, they have information on where you are, okay? The position. So this is not just A's and B, but they're actually like proper vectors. So you can compare where you are by appropriately defining this vector T, yeah, in order to maximize, okay, whether or not, so the last position of, yeah, just in order to make sure that you, so here you have this 5, for example, because you want to make sure that if A does not occur at all, then you get penalized. Remember, acceptance means less than 0, okay? So if you compute this thing at the end, you get that this is bigger than 0, which is not accepted, okay? Right, okay, so that's just to give you a quick illustration of how things work. So if you think about it, in order to just define A plus and B plus, the definition of the transformer is already quite complicated, right? So, and also I want to mention there are also some subtleties. So for example, like the attention mechanism, you saw that there's this, the unique height attention, so whereby you pick the leftmost vector with maximum score, and this average height attention transformers, where you average things out. And there's actually a couple of other things that I didn't mention. So for example, self-attention, which is more complex, and you use exponential functions. So this also, like, so Armando mentioned something like, you know, where you want to be able to associate probability values. So there you do need some self-attention. And this has been like less studied in formal language in FLAN, yeah, because it's, I think, quite complicated. And there's another thing that I kind of gloss over, which is positional encodings. So firstly, we do need to realize that we need positional encoding, because without positional encoding, almost the language that you recognize is pretty much order invariant. So I don't want to define this, yeah, almost. But it's very weak. You cannot really distinguish the order very much. And also in practice, non-trivial positional encodings are actually employed, for example, like sine, cosine, etc. So in our setting, this is, you might be a bit annoyed here. So in a lot of the settings in FLAN, we do allow any positional encoding, yeah, anything whatsoever. And even no computability is assumed. The point is that if something cannot be expressed, then it cannot be expressed, right? Even when something is computable, when the positional encoding is computable. So I think that's the one thing here that is important. So let me just go through a couple of things that are known. So one of the first results in the area is that parity cannot be expressed in UHAT. So this was proven by Michael Hahn in 2020, sorry. And he established a connection with circuit complexity. And about a couple of years later on, something stronger was shown by Howe et al. And Strobel, where they showed that UHAT is actually, the languages recognized by UHAT are subsumed by the circuit complexity class AC0. This basically language recognized by a family of constant depth polynomial size Boolean circuits. So it's one of the weakest languages you can find in complexity theory. And UHAT is also subsumed by AHAT, yeah? And in turn, this is subsumed by the circuit complexity class T0. And let me just mention, oh, sorry, I forgot to mention something. So it's known that parity is not in AC0, actually classic result by Aitai 1983. If maybe Moshe knows an earlier citation, I think this is the correct one. Yeah. And now T0 is an extension of A0 by the majority gates. The important thing about T0 is that you can do something more, like doing arithmetic and stuff like that. You need to go to T0 here. Now, not a lot. Well, something is known about T0, but like way less compared to A0. So for example, not all regular languages are in T0 unless NC1 equals T0. So let me just mention a couple of things that are important in the next step. So I mentioned that it's been quite difficult to, so if you want to just construct transformers with A plus and B plus, it's already quite difficult. So one natural question is, can you come up with a logic that can capture the language of AHAT languages, for example, so it can give you better grasp of what these transformers can express? And how do you connect this to regular languages? Which regular languages are in UHAT and AHAT? And how much counting can you do? And you can also go further to ask about other kinds of inputs, yeah, not just text. And I'm gonna mostly concentrate on the on the first three. So I will talk about descriptive complexity for UHAT. Let me just mention this quickly. Okay, so can I ask how many of you know, have some knowledge of AC0? And okay, so like half. Okay, so maybe what I'm gonna do here is I will just give a really brief overview. Right, so AC0 is a complexity class that has been studied quite a lot. So there's a lot of things that are known, connection to descriptive complexity, finite model theory, and we already know a logic that is connected to this. For example, this is the first order logic with arbitrary numerical predicates, yeah? So that's a classic theorem that AC0 is captured by precisely this logic. And you can do, for example, in order to establish this connection, you do need an encoding for this to structures. Yeah, so for example, you can encode it as such a structure, and this then you can express using first order logic. Yeah. Now, the question is that there is a need for some kind of numerical predicates in general. So these are like regular languages, but in general, this AC0 can of course go beyond regular language. For example, you can do AN B to N, where N is prime. Here you do need some kind of numerical predicates, obviously. So where you can talk about prime numbers. Yeah, so these are basically just any k-array relation, yeah, that is a subset of n to the k. There's no computability assumption that is needed here. And you can then, yeah, just define it like that, for example. That's one example here of a numerical predicate. And then you can then, appropriately, you can then say, okay, well, so then you can, in order to define this, you can simply take the last position for A and the last position for B, and then you can then just use this k-array relation. So now, okay, so we know that UHAT is in AC0, and we want to have a way of characterizing the language of UHAT with some logic, yeah? So how do you, what kind of fragment of AC0 is needed? What kind of fragment of FORP is needed? Now, in order to answer this question, firstly, is UHAT a strict subset of AC0? That's the natural question. So, so we observe that it's actually not so difficult to come up with such a language, and in order to separate UHAT and AC0. And the language, I'm not going to go through the detail, but this is actually one of the languages in Ajtai's paper, and you can then make use of the result of Han in order to show that this is not in up much. So this is not super difficult. Okay, so now in order to, so now we know that this is a strict subset. So we want to now come up with a subset of the of FORP where you can have this that can characterize UHAT. And the logic here that is needed is this FO-mon, yeah, where you only use monadic numerical predicates. That is here. This is a little example. So suppose you want to have this ANBM, where N and N plus M, yeah, these are prime numbers. So you can do something very similar, yeah, and you just simply have to talk about the last position of A's and the last position of B's, and just say that these are prime numbers. Okay, so that's how you do this. And our main result is FO-mon is a subset of UHAT. So it's not exactly equality, but we show that this is a subset of UHAT. Okay. Again, this is not a complete characterization, but we can show. So for example, like one can show that palindrome is in this UHAT, but not expressible in FO-mon. Yeah. So I have like about 5 minutes or 6 minutes. So UHAT, but not expressible in FO-mon. So let me just show something quickly. But there's one important corollary here. Namely that this can capture all regular languages in, so all regular languages in H0 can actually be captured by UHAT, yeah, namely because regular languages in H0, this was known to coincide with FO mod, where you have only it's first order logic, and you can express, you need to extend it with all monadic predicates that are of this form. Basically, these are modular counting predicates. In particular, they subsume LTL definable regular languages or star-free regular languages. And you can show that all regular languages in H0 are in UHAT here by using this, combining these two results. So I'm gonna really skip the proof, but I will just mention some proof idea here. So the proof idea is actually to make use of the connection between first order logic and LTL, yeah, and use something that is similar to Faraday-Wolper construction. So the idea is, instead of using FO1, you're now gonna use LTL because they are really the same thing here, but it's more like LTLF. Sorry, I need to correct it. So you can use Kamp's result that FO1 is equals LTLF here with monadic predicates, yeah. And then what you need to do is that you need to do inductions on the LTL formulas. So maybe I will skip the next slide here, but the main idea here is that you need to just simply extend the logic here with because these are monadic predicates, so you can think of it as just a proposition. Okay, so I think I'm not gonna go through the proof here, but the main idea here is that you need to let me just make sure here. I'll just show this part. Okay. So the main idea here is that when you're given a string A, B, 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 A, let's say, so you have a vector embedding, yeah. So by defining this embedding functions appropriately, so you're gonna get this vector embedding, and what you need to do at every step is that you're just gonna compute the value of satisfaction of any of the subformulas of the input formula, yeah, and then you're just gonna extend it one by one, yeah. Okay, and so on and so forth. And at the end, you're just gonna get a vector of truths for any of the subformulas. Okay, and that's basically the main idea. And then, yeah, you simply have to do the mathematics correctly. So I'm gonna skip the details here. All right, so maybe just a couple of remarks I'm gonna make. So there's a way to extend our approach here to capture palindrome. So it can be captured because the proof that we have, we can actually define it kind of independent of the ordering of the string. Yeah. So for example, in order to capture palindrome, you need to use this ordering 1, and you need to compare 1 and then the last one, and then 2, and then the second last one, and so on and so forth. So using this, you can actually express palindrome and express it in, for example, the following formula. Yeah. Okay, a couple of other things I want to mention super quickly. So we have something similar for AHAT, and in order to do that, we do need some counting, but counting on subformulas, and there's a linear arithmetic. So we can, for example, do A star, B star, C, D star, and then you can say like the number of A's plus the number of B's equals the number of D's. So this you can do, and this has some corollaries on the regular languages that are expressible in AHAT, but we don't really know yet, actually, if all of the regular languages are that captures that are definable in TC0 are also can be captured by AHAT, but we can at least show that permutation invariant ones are. Yeah. Okay, so I think I will skip this one. So we have some results also that extend this to time series data, but I think I'm happy to just talk about that at the end. All right, so I'm just trying to keep it within 30 minutes. So thanks.
So can you express palindromes?
You can express palindrome, yeah, using LTL with a different ordering on the position.
But in terms of regular languages, palindrome is really not regular.
Yes, we can express things that are not regular, right? Yes.
So why are we obsessing with regular languages?
Because other people obsess with regular languages.
But if it's obvious that your formalism express non-regular languages, the real question is, what is the expressive power of this? Yeah, it is somewhere between regular and context-free. Where is it? Well, that's the real question to me.
So first, we have to go back to the first question. I'm sorry that I went a bit too fast, maybe, but there was the first question. Okay, so people have a lot of problems trying to train parity, transformer for parity. So parity is definitely regular.
Absolutely.
So the question is like, why the hell can it not recognize parity, right? Well, actually, I didn't mention also the answer. So there was actually the answer to this, which is that actually there's a transformer for parity, yeah. But it's just that somehow it seems that it's not easy to train it. So there's no proof, yeah, that it cannot be trained. But people seem to have difficulties training parity somehow.
If you just try to train for parity,
yeah,
and you invest the same amount of training that went into training, let's say ChatGPT, you don't think you can train for parity?
Well, I mean, I don't know the answer to that. I don't think anybody knows the answer to that.
Nobody would want to spend that much money training for parity. That's the answer.
Sure. But I mean, like, it's just such a simple language, right? So you need to understand, like, why does it not work, right? So I think it's just like, it's just a scientific question.
Yeah, the answer would be to try to train for parity. Yes, and I'm not convinced that people have really said, okay, let's try to train for parity.
People have tried, actually. People have tried various regular languages. It's just the fact that it's expressible, it doesn't mean that you can train it. It doesn't mean that you can actually converse it. That the model will actually.
The result that says
no, we don't know. Like, but if people have tried to train, like, for example, sum of bit vectors, which is also regular.
I'm asking for parity, something very simple.
I think also for parity, it's unclear whether you can. I think for any language, the fact that it's expressible, this is my follow-up language, is like, we know that these are universal approximators in the general sense. So I don't understand also a lot of these results exactly what they're studying. Like, even with neural networks, we know they're universal approximators. So what is exactly that you're interested in terms of expressiveness? Is like any Boolean function, technically they can approximate it, right?
Well, I mean, here,
if you allow positional encoding and everything, the people.
The problem with the parity is how to approximate parity, right?
Well, you can get it 50% right.
Yeah, you get, so basically the answer is about 41. So. So there was a comparison between, so basically people were trying to train for parity and they're comparing it transformers and RNN, for example. So RNN, they managed to get quite high, but then transformers like always like between like 40 to 60%. So which is not very good.
No, but in general, you can, the universal approximation results is just like you can get arbitrarily close, right? It's like you just need to add, I think there is a question of.
It's not that obvious. So because I think they actually use a lot of, but this depends on the expressive power of your formalism at the beginning, right? So if you want to be able to get something very, very close, then you need to make sure that the model.
Yeah, but in your expressive power, you are giving up some of the real expressive power. Like you're putting ReLUs, you're doing some of other things, right? Like, because the universal approximation results, even for normal neural networks, initially it was just with sigmoid, but then they showed even with ReLU, you can get universal approximation. You need very, very big models. So that's kind of why I'm getting a little lost here on is the result that you want exactly the function and not an approximation?
Well, I think that's basically the question for now. Yes. Yeah. Okay.
I guess maybe to follow up on the point that Loris made, I guess there are all these results about these being universal approximators, but I think what's different here is that we're talking about unbounded sequences. So I don't think any of those results apply to unbounded sequences.
This is why I wasn't really sure about this as well. Yeah.
You can go there and encode them. Like, I mean, we know sequences can be encoded into integers, and then it's another function that can So I don't know, but it's
I think if you were talking about sort of real numbers, then like, yes, sure, right? You can encode the infinite sequence as this infinitely precise real number. But we're not talking about infinitely.
that I can encode through auto encoding or something else into an integer, and then I can change it to different integers. I don't know. I'm kind of guesstimating a little bit here, but finite sequences, they don't bring you out of integers, right?
Sure, but I think what you're talking about here is training a function on some finite set of sequences and then being able to generalize to unbounded sequences, right? Even sequences that are, potentially orders of magnitude longer than the sequences you trained.
Yeah, so I don't have a good answer to your question, but I think the unboundedness of the length makes a difference, and also like there's also the precision, arbitrary precision also makes a difference. Yeah, of course, also the model makes a difference. So that's I mean, I don't think this is a clear-cut answer.
I had a very similar comment. So the universal approximation results that I know is from Rn to Rm. If your function is from Rn to Rm, from a finite dimensional vector space to another finite dimensional vector space, you have universal approximation. But once you start talking about sequences, you are in an infinite dimensional vector space. Then
Where's it in? Yeah.
you always have a finite window.
Well, I mean, it is, in theory, it isn't it? Well, it's, I mean, you can compare like, this position to any other things that are quite far away, right?
Context window is finite.
Yeah, the context window is finite in the sense that you, so, yeah, but still, I still don't see this clear-cut answer here. I think for RNN, it's way simpler because you only have always you always like, read the next one, but here you can really look really far away, so.
So maybe that's discussion that you can continue also over lunch.
Yep.
So let's thank speaker once again.
Thanks a lot.
And we break now for the lunch, and we meet again